Hello my lovely students, you are welcome to a new lesson. Today, I shall be teaching you approximation and errors. This is the map of Nigeria. Nigeria has a population of approximately 200 million people. Nigeria has approximately 250 ethnic groups. Nigeria has approximately 500 languages. All these values are approximated figures. Let's learn more about approximation. From definition, approximation is the process of using rounded values when presenting numerical data and making rough calculations. Please note that we have 10 digits, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Of these 10 digits, the first 5 digits, which are 0, 1, 2, 3, and 4, are rounded down to 0. These are the round down digits. The last 5 digits, which are 5, 6, 7, 8, and 9, are rounded up to 1. These are the round up digits. Let's look at the 3 forms of approximation. Number 1, significant figures. Significant figures are counted from the first non-zero digit of a number. Number 2, decimal places. Decimal places are counted from the decimal point. While number 3 is place values. We can approximate numbers to nearest whole number, which is units, nearest 10, nearest 100, nearest 1000, nearest million, nearest billion, and so on. Please take note of this information concerning approximation. Moving on, let's see our first example. Example 1. Round up the number 163.864 to 2 decimal places, 1 decimal place, the nearest whole number, and the nearest 100. Let's see the solution to question 1A and B. In question 1A, we are to approximate the number to 2 decimal places. Don't forget, we count the decimal places from the decimal point. So the second digit after the decimal point is the digit 6. The next digit to the right of 6 is 4. That is a round down digit. Round the 4 down to 0 and add 0 to 6. That will give us 6 in the second decimal place, while the next digit to the right becomes round, which is a 0 digit. The answer to question 1A becomes 163.86 to 2 decimal places. For question 1B, approximating the number to 1 decimal place, the digit occupying the 1 decimal place, that's the digit after the decimal point, is 8. The next digit to the right of 8 is 6. Round up 6 to 1 and add 1 to 8. That steps up the 8 to 9. And every other digit to the right of 8 becomes round, which is 0. That gives our answer to question 1B as 163.9 to 1 decimal place. Don't forget, the extreme zeros at the right of the number, they are not significant after the decimal point. So we are going to disregard the extreme zeros after the decimal point in the answers. Moving on, let's see the solution to question 1C and D. Now, can you tell the answer when 163.864 is approximated to the nearest whole number and to the nearest 100? Let's see if you can. The answer to question 1C is 164 to the nearest whole number. Here we have to round up to get this answer. For question 1D, the answer is 200 to the nearest 100. Here we have to round up again to get our answer to question 1D. I hope you got these answers correctly. Looking at our second example, example 2, round off 0.002487 to one significant figure, two significant figures, and three significant figures. Looking at the answers, can you still remember how we count significant figures? Of course, we count significant figures from the first non-zero digits. That makes the answer to question 2A to be 0.002 to one significant figure, because the first significant figure is 2. That's the first digit after the zeros at the left. We have to round down to get this answer. For question 2B, the answer is 0.025 to two significant figures. This is so because the second significant figure is 4 in the number. Of course, we have to round up the 8 next to 4 to 1, and adding it to 4 will give us the 5 in the answer. So the answer is 0.0025 to two significant figures. Lastly, the answer to question 2C is 0.0249 to three significant figures. Here we have to round up to get this answer to three significant figures. Let's take our third question. Example 3. Round off 6.0995 to three significant figures and three decimal places. Now, looking at this question closely, can you tell the answer to three significant figures and three decimal places? Let's see if you can. For question 3A, approximating the number to three significant figures, the third significant figure is 9 after 6 and 0. So the first 9 is the third significant figure. The number at the right hand side of 9 is another 9, which is a round up number. Round up the 9 to 1 and add it to the 9 in question in the third significant figure position. That gives a 10, which we have to put down 0 and carry 1 to the left. So that makes the approximated answer 6.10 to three significant figures. Here we have to write the last 0 in the answer because we need three figures. So we have to write 6.10 as our answer to three significant figures. For question 3B, the answer after rounding off 6.0995 to three decimal places is 6.100 to three decimal places. Here we have to keep the extreme two zeros in the answer because we need three figures after the decimal point. So the answer is 6.100 to three decimal places. Please take note of the answers in question 3. Moving on, let's learn about errors. From definition, error can be described as a value that gives the range of values where the true or actual value of a measurement is found. Whenever we approximate values, we introduce error into the value. Error can be positive or negative. We have three types of errors. Number one is the absolute error. Number two, relative error. While number three, percentage error. Let's learn more about these three types of errors. Number one, absolute error. From definition, absolute error or degree of accuracy is the difference between the measured value and the true or actual value. That means that the formula for absolute error is number one, the absolute error is the measured value minus the true value. The second formula is absolute error is plus or minus half of the degree of accuracy in the approximation. Looking at the second type of error, number two, relative error. This is obtained by dividing the absolute error by the true or actual value. That means the formulas for relative error are number one, relative error is equal to the absolute error divided by the true value. That's the same thing as relative error being equal to the measured value minus the true value divided by the true value, as well as relative error also being equal to plus or minus half times the degree of the accuracy divided by the true value. Looking at the third type of error, number three, percentage error. Percentage error is the percentage of the relative error. The formulas for percentage error are as follows. Number one, percentage error is equal to relative error times 100%. Number two, percentage error is equal to the absolute error divided by true value times 100%. Number three, percentage error is equal to measured value minus true value divided by true value times 100%. While number four, percentage error is also equal to plus or minus half times the degree of accuracy divided by true value times 100%. Please take note of these formulas for the different types of errors. Now let's see some examples involving errors. Example 4. A rope of length 1.75 meters was measured by a boy as 1.80 meters. Let's find the absolute error, relative error, and the percentage error in the measurement. Now, can you remember the formulas for the absolute error, the relative error, and the percentage error of a measurement? Let's see if you can. For the solution to question 4a, in question 4, the true value is 1.75 meters. That's the actual value of the rope, while the measured value is 1.80 meters. Now, talking about the absolute error, the formula is measured value minus the true value. Subtracting your values, the absolute error in question 4 is 0.05 meters. For question 4b and c, to calculate for relative error, the formula for relative error is the absolute error divided by the true value. That gives 0.05 meters divided by 1.75 meters. So our relative error is 1/35 or 0.02857. Please take note there is no unit in the relative error because the meters has cancelled out in the division. The percentage error, the formula is relative error times 100%. Multiplying the relative error by 100%, our percentage error is 2.857% or 6/7%. In question 4, we can see that the errors are all positive. Talking about the absolute error, relative error, and percentage error in question 4. This is so because the measured value is greater than the true value. Moving on to our 5th question. A sales girl gave a change of 115 naira to a customer instead of 125 naira. Calculate her absolute error, relative error, and percentage error. In this question, can you tell the true value and the measured value in this question 5? Let's see if you are correct. For a solution to question 5a, in question 5, the true value is 125 naira, while the measured value is 115 naira. So to get the absolute error, we are going to calculate measured value minus the true value. That will give us a negative error, which is minus 10 naira absolute error. This error is negative because the measured value is now smaller than the true value. Looking at solutions to question 5, B and C. To know the relative error, the formula is absolute error divided by the true value. That gives us minus 10 naira divided by 125 naira. Our relative error is minus 0.08. Please take note once again, there is no unit in the relative error because the unit, which is the naira signs, has cancelled out. Lastly, to know the percentage error, the formula is relative error times 100%. Multiplying your relative error by 100%, our percentage error in question 5 is minus 8%. If you can observe closely, you will see that all the errors in question 5, they are all negative errors. Once again, this is so because the measured value is smaller than the true value. I hope the solution to question 5, they are clear to you. Let's look at our last example, which is example 6. The length of a running track is measured and given as 400 meters to the nearest 10 meters. Question A. What is the range of its actual length? Question B. Calculate the percentage error. Now, to know the solution to question 6a, the formula for range is the true value plus or minus the absolute error. In question 6, the true value is 400 meters. Now, to know the absolute error in question 6, the approximation in question 6 is to the nearest 10 meters, which is to the nearest tens. That makes the degree of accuracy in question 6 to be 10 meters. Now, the absolute error, the formula to apply here is half of the degree of accuracy. So half times 10 meters will give you an absolute error of 5 meters. Please take note of the way we calculate absolute error in such a question. Here we are not applying measured value minus true value. Here we are applying half times the degree of accuracy. Please take note of these facts. Now for question 6a, what is the range of its actual length? The range is the true value plus or minus the absolute error. That makes 400 meters true value plus or minus 5 meters absolute error. Now I'm going to subtract first to get the lower limit of the range, which is 400 meters minus 5 meters. That will give us 395 meters. While we will add later to get the upper limit of the range. That is 400 meters plus 5 meters. That will give us 405 meters. That means the range of actual length in question 6a is 395 meters to 405 meters. To know the solution to question 6b, to calculate the percentage error, the formula for percentage error is the absolute error divided by true value times 100%. That makes the percentage error to be 5 meters divided by 400 meters times 100%. Our percentage error is 1.25%. I hope the solution to question 6 they are clear to you.
Thank you very much for going through the lesson today. I want to advise that for you to get more information about the topic approximation and errors, please continue to read your textbook. Don't forget to attempt your quiz and your assignment. I hope to see you again in our next class. Until then, it is goodbye for now. Thank you very much.